Good morning. I welcome you to this session of fluid mechanics. In the last class, we were discussing the steady uniform flow through a straight channel, and we developed an expression for the average flow velocity in the channel. So, if we recall the discussion, we see that we considered a straight rectangular channel with a slope. This is the slope with the horizontal, this is the channel, and what we did, we took a control volume where we found that the pressure forces on these two surfaces balance each other. So therefore, the net force acting on this is the difference between the frictional force at the surface of the channel, that is the bed of the channel, and the weight. And since the flow is uniform, so we made the equation, the use of the equation that the net force acting in the direction of flow, that means the component of the weight and the frictional forces, to be 0. And ultimately, we equated that and we found an expression. Before that, the wall shear stress was expressed in terms of the friction coefficient and the average velocity of flow in this manner. And finally, we arrived at the equation V average is CRH S whole to the power half, where this C is given by root over 2G by F. This is C. So therefore, C is 2G by F whole to the power half. So this was defined as Chase's coefficient, and this equation is known as Chase's equation, where RH is the hydraulic radius and S is the slope of the channel, which is equal to sin theta or tan theta for small values of theta. That is the angle between the bed or base of the channel with the horizontal. Now in this equation, one thing, the Chase's coefficient is unit is, you see F is free dimensionless, so it is g to the power half, that means meter divided by second to the power, meter to the power half divided by second, meter to the power half divided meter to the power half divided by second, that is the unit of C. Now we should know what are the factors on which the C depends. So you know C is defined as 2G by F. As we have already discussed in case of pipe flow, that is F friction factor depends on Reynolds number of flow and the relative roughness, that means the roughness divided by the diameter or the hydraulic diameter of the pipe. Here in the similar fashion, this Chase's coefficient C also depends, that means becomes a function of Reynolds number of flow and the relative roughness defined as the roughness divided by the hydraulic radius. We have earlier discussed about the Reynolds number. The Reynolds number is defined in this case as rho times the average velocity times the hydraulic radius divided by mu. In case of turbulent flow, when Reynolds number is greater than 600, the Chase's coefficient depends on the average roughness coefficient. So therefore, dependence on Reynolds number is actually not there in case of turbulent flow. In all practical cases, flow is turbulent, so therefore the Chase's coefficient depends only on the absolute roughness, or we can tell the roughness and the hydraulic radius. So these are the factors on which C depends. Now I will show you certain empirical formula for the Chase's coefficient C, which is a function of the N is the roughness factor here and RH is the hydraulic radius. It is mostly the function of the roughness factor and the hydraulic radius. First one is that due to Ganguillet-Coulter GK formula. These are all empirical formula. Here of course the slope of the channel S comes, but in other formulas this C, that is due to Pavlovsky formula 1 by N RH to the power OI. This is OI, RH to the power OI, where OI is given by this function. So RH is the hydraulic radius. Another one is Manning's formula. Manning's formula 1 by N RH to the power 1 by 6. I am writing it again, it is very important, 1 by N RH to the power 1 6. Now these are all empirical formulas where N, the roughness factor, if it is expressed in meter, we get the value of C in its dimension as we have seen earlier, meter divided by meter to the power half divided by second. Okay, so amongst all these formula, it is found that this Manning's formula, this is the Manning's formula, this is written again here, is the simplest one and it is fairly accurate. So therefore Manning's formula is in popular use, 1 by N RH to the power 1 6. Now, one interesting feature can be observed from this formulae, that all these empirical formulae gives the same value of same value of Chase's coefficient C as 1 by n when RH is equal to 1. That means that unique hydraulic radius, the value of C is 1 by n. That means if we put RH is equal to 1 in this equation, RH is equal to 1 either in this equation is clearly seen 1 by n. So, all these three equations show the value C is equal to 1 by n. Now, if we use the Manning's formula which is the most popular one because of its simplicity and fairly accurate in nature, we can write with this Manning's formula 1 by n RH to the power 6. If we take this, we can write here V, okay, we can say there that V, earlier we deduced V is equal to V average is equal to, in place of C we write 1 by n into RH to the power 1/6, then RH is to the power half. What we are doing? We are using this expression, V average is C RHS whole to the power half, and in place of C we are writing 1 by n RH to the power 1/6 from the Manning's formula. So, therefore, we come to this value V average 1 by n RH to the power 1/6 RHS to the power half. Now, this can be written in, if we now express RH in terms of A by P, then what we can write? Before that, I think RH 1/6 and half, this becomes, this is RH 1/6 plus half, that means 1 plus 3, 4 by 6, that is RH 2/3 S to the power half, okay, RH 2/3 S to the power half. And if I write A by P, then we can write 1 by n A to the power 2/3 by P into S to the power half. And if we write the discharge Q, which is equal to A into V average, the cross sectional area, so A is multiplied, we can write 1 by n A to the power 5 by 3 divided by P to the power 2/3 divided by P to the power 2/3 S to the power half. Okay, so this is the expression for the volumetric flow rate. So, you see the volumetric flow through the channel or the flow average flow velocity is a function of the cross sectional area, the perimeter, and the slope of the channel and the roughness factor. Here I can show you the roughness factor for different materials of construction for the channels, the type of surface, values of Manning's roughness coefficient in, for straight uniform channels, for smooth cement, plain timber 0.01, rough timber canvas 0.012. So, these are the cast iron, good ashlar masonry brickwork 0.013. So, we see that tables are available from where we can find out the values of n depending upon the type of surface for the channel bed. Now, if we see this Q is equal to this formula, now this gives the rate of discharge as a function of the geometrical dimensions of the channel. Now, and one important application of this formula in the design of artificial canals is optimum hydraulic cross section. Optimum hydraulic cross section. Optimum hydraulic cross section. What is this optimum hydraulic cross section? Optimum hydraulic cross section is the cross section which gives for a given cross sectional area the maximum discharge, or for a given discharge and given cross sectional area the minimum perimeter. The cross section of the channel which gives the maximum discharge for a given cross sectional area, that means the minimum weighted perimeter for a given discharge and a given cross sectional area, is known as the optimum hydraulic cross section. Here the discharge is maximum for a given cross sectional area, and also we can say from other angle for a given discharge the perimeter is minimum. So, this is sometimes known as economic proportioning of cross section, economic proportioning of cross section. Why it is known as economic? Because if we see from this angle of the minimum perimeter, which means for a given discharge, if the weighted perimeter is minimum for a given cross sectional area, then we require minimum lining material to be added to the channel bed and the channel surface. So this pertains to the word economic. So it is economic proportioning of cross section or optimum hydraulic cross section that gives the maximum discharge for a given area, or for a given discharge the minimum weighted perimeter. Now out of all sections, we know that a semicircular section gives a minimum weighted perimeter or a minimum perimeter out of a given cross sectional area, out of given area. But it is not used for different constructions from some practical difficulties, though it can be built from prefabricated sections, but it is not in use. Most popular section is a trapezoidal section. Most popular section is a trapezoidal section. So therefore we will find out the condition for an optimum hydraulic cross section for a trapezoidal section. Now let us review again the condition that A by P should be made maximum, that weighted perimeter has to be made minimum. Now if we define the hydraulic radius RH as A by P, then we can say that for a given area P is minimum means RH is maximum. That means the cross section will be such whose hydraulic radius will be maximum for a given flow. Now let us find out what is this condition for a trapezoidal section. That means we consider a trapezoidal type of cross section for the channel. Let us consider this is the trapezoidal section, and this dimension is given by this, the width is B. Let us consider the depth of flow is H, the central depth of flow is H, and the side slopes are alpha. The trapezoidal sections are defined by these geometrical parameters with central depth of flow as H. Now what is this area of cross section? Now we see that if we make a perpendicular here, so this is from the geometry, so this is H, so this is alpha, so this is H cot alpha, this much. Similarly this length of this side is H cosec alpha. So area is B into H, that means the rectangle B into H plus this one, the triangle, the two triangles, that means H square cot alpha plus H square cot alpha. What is the perimeter P? Perimeter is this width B at the base plus this length plus this length. That means B plus 2H cosec alpha. Now from here we can find out that RH is A by P, but we will have to eliminate this B from here. So if I eliminate B from this equation, A by H minus H cot alpha. Now I can write RH is equal to A by P. Now what is P? P is this one, but I replace B from this. That means I have eliminated B from this equation as this. Now the value of B from this equation is replaced here in terms case of P. That means A by H minus H cot alpha plus 2H cosec alpha. All right. So this is the value of RH. Now you see that this is the value of RH. Okay. Now for a maximum of RH for a given area, area is constant, means the minimum of the numerator. So we try to find out the minimum value of the numerator for the optimum trapezoidal section. Now what are the variables? Now if I find out this condition for a particular depth, that means we try to find out that at what depth of flow this will satisfy the condition of maximum RH, that means the minimum of the denominator. That means the maximum of the RH means the minimum of the denominator. Okay. So therefore I differentiate the denominator A by H minus H cot alpha plus 2H cosec alpha to be 0 to find out the minimum condition for the denominator. Let us do it. We will get minus a by, that means if we consider the geometry to be fixed, alpha fixed, differentiate with respect to h, minus cot alpha plus 2 cosec alpha is equal to 0. From where we get a is equal to h square 2 cosec alpha minus cot alpha, that is a. Now, if this value of a we just put in this expression of RH. Now, let us again write this expression RH separately, otherwise difficult to follow. RH is a by h minus h cot alpha plus 2h cosec alpha, that is RH, and we have got a is h square 2 cosec alpha minus cot alpha. So, if I put that value of a, which we have got h square 2 cosec alpha minus cot alpha, 2 cosec alpha minus cot alpha. So, this is the value of h. So, if we put here, it will be h 2 cosec alpha minus cot alpha h, then minus h cot alpha plus 2h cosec alpha. So, if you make it clear, so you will see that numerator will be 2 cosec alpha, you make some algebraic manipulation. So, denominator will be 2h, if you take 2h common, then it will be like this. So, this cancels, so this ultimately h by 2. So, therefore, the result is that RH is h by 2. That means the hydraulic radius will be equal to half of the central drain. This is the conclusion for the case that optimum hydraulic section for a trapezoidal section, the hydraulic radius will be half of the central depth of flow, h by 2. Now, here we can develop a particular relation that in case of a rectangular section, you see that what is the rectangular section defined from a trapezoidal section is the special case when alpha is 90 degree. That means this is perpendicular to the base. In that case, what is the value of a from here for the maximum RH condition? That is a is equal to 2h square if you put alpha is equal to 90 degree. One thing you must know that we have talked about the minimum of that. That is obvious because I have said the first differential is 0 and this is the first differential with respect to it. So, second derivative is obviously positive because these two terms will not appear. So, this will give a positive term, which means this expression has a minimum with the variation of h. For h, this has a minimum only. So, that is proved. Now, a is equal to 2h square for a rectangle. So, for a rectangle, a is equal to 2h square. And again RH is equal to h by 2. So, this is the condition that RH is equal to h by 2 and a is equal to 2h square. So, immediately from this one thing comes, if a is equal to 2h square, then the width of the rectangular channel will be 2h square by h, because h is the depth of flow, which is the height, that means this is the rectangular channel. So, if this is h, so therefore, if B is this width, so if B is this width, so area is 2h square, area is B into h divided by this h will give you B, which is equal to 2h. That means the width of the rectangular channel will be twice the depth of flow. All right. Now, if we see that we maximize RH or minimize this denominator with respect to h. Now, if we consider that the depth of flow remains constant and we vary this angle for the trapezoidal section to find out at what angle the RHS is maximum for the optimum hydraulic cross section. That means the denominator is minimum. In that case, we will have to differentiate this quantity with respect to alpha and is set to 0 instead of h. If we do it, then we will see, if we do it, then we will see if we differentiate it with respect to alpha, that means this quantity, without differentiating, that means if we write dd alpha of this quantity, a by h minus h cot alpha plus twice h cosec alpha, then we find dd alpha, then we find that is equal to minus h cot alpha, so h cosec square alpha minus 2h cosec alpha cot alpha, because the derivative of cot alpha is minus cosec square alpha and cosec alpha is minus cosec alpha cot alpha. And if we put this is equal to 0, that means h cosec square alpha minus 2h cosec alpha cot alpha is 0, we get simply cos alpha is half, which means alpha is 60 degree. That means we get a trapezoidal channel with this angle as 60 degree, which is half of a regular hexagon, half of a regular hexagon. So this is the angle. So half of a regular hexagon, because hexagon, regular hexagon, these included angles are all equal to 120 degree. So this is half of a regular hexagon. So this cross section given by alpha is equal to 60 degree, half of a regular hexagon, for a given depth of flow pertains to the optimum hydraulic cross section for a trapezoidal section, that means the maximum of hydraulic radius RH. Okay, now we will discuss a new topic, that disturbance of wave, small disturbance, propagation of waves, propagation of waves, propagation of waves, propagation of waves by small disturbance, by small disturbance, propagation of waves by small disturbance in a channel, in open channels, in open channels. Now let us see what is meant by that. Now you know, in a pool of water, for example any pool of water, if you make a disturbance, that disturbance propagates in the form of wave. That means a wave is generated and the disturbance propagates from the source of disturbance where it is created in both upstream and downstream directions in the form of wave. Just an example, we can say that if in a river or a pond, if we put a stone, drop a stone, then you see that waves are created. The stone where it is dropped, it creates a disturbance and automatically waves are generated, and by which the disturbance wave is ultimately propagated to the entire liquid mass. Similar is the case when in a river, if we open or close a sluice gate, then you will see a disturbance is created which is propagated both upstream downstream in the form of an wave. So therefore a small disturbance created in a pool of liquid, which either it is stagnant or it is flowing, a disturbance creates a wave which is propagating through this fluid medium. Fluid medium may be stagnant or may be moving. Now our first job is to find out what is the propagation velocity of this disturbing wave, or the propagation velocity of the wave created by the disturbance. Let us consider that, propagation velocity of the wave. For that we consider a rectangular channel, rectangular channel, we consider uniform flow, uniform flow, uniform and steady flow. We consider an uniform steady flow through a rectangular channel of nearly zero slope, that means whose bed is almost horizontal, nearly zero slope. And we want to find what is the propagation. Our main objective is the propagation, main objective is to find the propagation velocity of the wave, of waves caused by disturbance, waves caused by small disturbance, caused by small disturbance. In this regard, I tell you that one terminology, that a wave is considered positive if it increases the height or the depth of flow. If it increases the depth of flow, it is considered to be negative if it reduces the depth of flow. We consider a positive wave for our analysis. Now let us consider a rectangular channel like this. Now you see, when the wave is moving through this flow, the channel, then what happens, the downstream conditions with respect to the flow, or we can tell the region of the flow through which the wave has already traveled has changed its hydrodynamic parameter, like the flow velocity and the depth, where the upstream flow velocity and depth, which was the undisturbed flow velocity and depth, is yet to suffer a change. Let us consider this is like this. H1 is the upstream depth, which is undisturbed depth, and V1 is the velocity. And let us consider that this is the downstream depth H2 and the velocity is V2. So the velocity is changed as the wave propagates. Let us consider at any instant this is the position of the wave, which is propagating upstream with a velocity c. At any instant this is the position of the disturbing wave, which is propagating with a velocity c in the upstream direction. And so that the with respect to this wave, this is the downstream, this is the upstream. With respect to the flow, this is the upstream and this is the downstream. So with respect to the flow, we can tell the upstream conditions for depth of flow and velocities are undisturbed and remains as H1 V1, which are changed to H2 V2. For a positive wave, the depth is increased to H2 and the velocity becomes V2. Velocity will be reduced because the depth is increased, H2 and V2. So this is the condition we just can see at any instant. Now if we want to analyze the situation through the application of the momentum theorem, then what we have to do, we have to take a control volume surrounding this wave. So if I take this control volume separately in this, we will show the control volume like this. If this is like this, we take a control volume like this surrounding this wave. Now we have already discussed that for this type of case, the control volume is considered to be fixed with this moving object. Here the moving object is the disturbing wave. Why? This is because if we consider the entire thing with respect to this, analyze with respect to this wave, then what happens? The things become steady. Otherwise the things become unsteady. Just for example, you see at any point in the fluid here, now the velocity is V1. When the wave passes through this point, the velocity will be changed to V2, or the depth will be changed from H1 to H2. So with respect to time, a point suffers a change in its hydrodynamic parameters, that means in unsteady flow. But what we do instead, if we impose a velocity c in opposite direction, that means in that case if we consider the fluid is moving with a velocity V1 plus c in this direction and V2 plus c in this direction, and wave is stationary at a particular location, then what happens? The flow becomes steady. That means for all points here, the velocity is V2 plus c, which is invariant with time, and for all points in this region, velocity is V1 plus c is invariant with time, which is invariant with time. So therefore, for this purpose, we make an analysis with respect to the standing wave. That means the coordinate axis is attached to this, to this moving wave. The coordinate axis is attached to this moving wave. Or in other words, we tell that wave is mesh stationary by superimposing a velocity c in the opposite direction to the entire system. So in that case, we see that if we designate the control volume as A, B, C, D, so the fluid comes through the face AD with a velocity V1 plus C, and the fluid leaves the face BC with a velocity V2 plus C. This is simply the picture. Now you see what happens. What is this is H, this is H1, and this depth is H2. Now you see the flow is uniform. So flow is not uniform here. I am sorry, V1 plus C to V2 plus C. Now you write the control momentum theorem for the control volume. That means the net force acting on the control volume is equal to the net rate of momentum efflux in a specified direction. We take this direction, the direction of flow, to be the specified direction. What is the force acting in this direction? One force is the force which is acting on this surface due to hydrostatic pressure. Similarly, on this surface, the force acting in this direction is the hydrostatic pressure. Let this force is F1, this force is F2. And if we consider this control volume to be small, that means this distance to be small enough, because the wave is very thin. So here it is shown in the diagram in a very exaggerated way. Actually, this width is very small, so that the frictional force can be neglected as compared to these other forces, hydrostatic forces. But the thing is that the hydrostatic force here is due to the static pressure variation in this fluid throughout this height h1. So what is that value? We have already discussed this in fluid statics. This F1 will be rho g h1 by 2 into h1. If we take an unit dimension in the direction perpendicular to the plane of the paper, then we can take that this is h1. That means width is unit, width of the channel if we take unit. Then rho g h1 by 2 is the pressure intensity at the centroid, and then area is h1. So simply rho g h1 square by 2 is the hydrostatic pressure force on this surface AD of the control volume. That is due to this part of the liquid, that means this part. Similarly, F2 is the hydrostatic pressure forces in this part of the liquid, which is equal to rho g h2 square by 2. So therefore, the net force acting in this direction will be F1 minus F2 is equal to rho g h1 square by 2 minus rho g h2 square by 2. Now, what is the change in momentum in the direction or momentum A flux for a control volume? The statement will be net rate of momentum A flux in this direction. It is mass, that is rho q, into the change of velocity, that is v2 plus c minus v1 plus c, and that must be equal to, according to the momentum theorem, h1 minus rho g h2 square by 2, or we can write rho q v2 minus v1 is equal to rho g h1 square by 2 minus rho g h2 square by 2. All right. Now we see that what is q? Q can be written as q is equal to area into velocity. So therefore, q can be written as v1 plus c into h1, or is equal to v2 plus c into h2. So if we now want to express everything in terms of v1, what we will do? We will eliminate v2 from here in terms of v1, which is v1 plus c into h1 by h2 minus c, h1 by h2 minus, and replace q in terms of v1, v1 plus c into h1 in this equation. That means then we get rho into v1 plus c into h1 into v2. What is v2? v2 is v1 plus c, we can make a second bracket, into h1 by h2 minus c minus v1, and that becomes is equal to rho g by 2 h1 square minus h2 square. So we can write this rho v1 plus c whole square. If we take v1 plus c common, then h1 by h2 minus 1 is equal to rho g by 2 h1 square minus h2 square, from which we get that v1 plus c whole square. If we take this h1 minus h2, there what we get? We get h1 minus h2, that is h1 plus h2 into h2 by h1. So therefore, we get v1 plus c whole square is h2 by h1 into g is there into h1 plus h2, or we can write gh2 into 1 plus h2 by h1. Well, so v1 plus c is equal to gh2 to the power half into 1 plus h2 by h1 to the power half. So this is the expression for v1 plus c, gh2 to the power half into 1 plus h2 by h1 to the power half. Okay. So this is okay. There is a 2 was missing, so 2 will be there. So divided by 2 to the power half, or what we can write here, half into 1 plus h2 by h1, and we can make a second bracket. Okay, fine. So we can write it again, that v1 plus c is equal to gh2 to the power half into, we can write 1 plus h2 by h1 by 2. That means 1 plus h2 by h1 by 2. We can write this fashion to the power half. This is the expression. Now, if we consider the height of the disturbing wave is small, which means that H2 minus H1 is very less, is almost 0, or H2 is very close to H1. That is a small height of the wave. For a small disturbance, small height of wave. That means wave height is very small, where the difference in depth of flow is very less, H2 is H1. So, then we can put this is equal to 1. So, this becomes 1. In that case, V1 plus C becomes the depth of the. That means for a limiting condition, that small height wave, that H2 approximately equal to H1, we get this expression. This is a very, very important expression. What does it then physically signify? This signify that this is the propagation velocity. That means if this is the channel, okay. So, this is the velocity C, that is the propagation velocity of the disturbing wave. So, V1 is the flow velocity in the channel. So, therefore, V1 plus C is the relative velocity of the wave with respect to channel velocity, with respect to flow velocity of channel, flow velocity in channel. That means this V1 sorry, channel. That means this V1 plus C is the velocity of the wave relative to the velocity of the fluid in the channel, which is equal to GH to the power half. So, this is a very important conclusion, that in case of a wave generated by a disturbance, this propagates in the fluid in both upstream and downstream direction, whose magnitude with respect to the flow velocity in the channel is given by GH to the power half, where H is the depth of flow. Okay. Now, next I will start the concept of specific energy. Concept of specific energy. Concept of specific energy. Now, you know the total mechanical energy in a fluid is the sum of the kinetic energy plus the potential energy because of its exposure or position in a conservative body force field. If we consider gravity is the only body force field, so it is the gravitational potential energy plus the pressure energy. And energy per unit weight is the total mechanical energy per unit weight or total mechanical head. Now, to measure the potential energy, kinetic energy is given by mass times velocity square by 2. The pressure energy is given per unit weight is P by rho g, or per unit mass is P by rho. Now, to measure the potential energy, we have to fix a reference datum from which the potential energy has to be measured, and that datum, the potential energy is 0. So, potential energy is given by mg into z, where z is the height from that reference datum of the system concerned. Now, in a channel flow, you see certain things just like this. Let us consider a channel. Let us consider a channel flow of some slope theta. Let us consider this is a straight channel which is flowing with a free surface, and this is the depth of the flow. Now, if we consider any reference datum, and then one thing is very clear, that for any point in the channel, if at that section the depth is h, so at this point what is the sum of the pressure energy plus the potential energy from this datum? So, that is equal to, if this is z plus z, the plus z. Okay. So, therefore, we see that the pressure energy is equal to this A P by rho g plus H. Now, what is this A P by rho g? P by rho g is this vertical distance, because if we consider this P by rho g, that from the atmospheric pressure. So, this vertical distance, let this is called Z1. So, therefore, this becomes Z1 plus Z. That means always it is the height from the reference datum of the free surface of the fluid which represents the sum of the pressure energy and the potential energy of any point in that section. So, therefore, if I know the depth of flow at a particular section, then the vertical distance or the vertical height from the reference datum for up to the free surface at that section represents the sum of the pressure energy and the potential energy for any point in that section. Now, specific energy is the sum of all the energies per unit weight, that means ES is sum of all the energies per unit weight, that means P by rho g plus V square by 2g per unit weight plus Z provided the potential energy is measured from the bed of the channel, from the bed or base of the channel. Now what happens at any point if I measure the potential energy by this height, that means let this is Z, then this is Z, okay. Then V square by 2G is all right. So what is P by rho G? This is P by rho G. That means therefore we see that in this case it becomes the depth of flow. So therefore these two, P by rho G and Z, this considered the depth of flow, okay. So therefore we can write that ES is equal to depth of flow plus V square by 2G. So therefore according to the definition, the specific energy is the sum of all the energy, mechanical energy, pressure energy, kinetic energy and the potential energy per unit weight. That means it is a total mechanical energy per unit weight, where the component potential energy is measured by the height from the bed of the channel. That means the bed of the channel with its respective slope is considered to be the reference datum. So in that case, Z, the potential energy plus the pressure energy which is measured from that above the atmospheric pressure is P by rho G. So these two constitutes the depth of flow at any section. So therefore the specific energy at any section is H plus V square by 2G, where V is the average flow velocity at that section, or for a point then it will be the velocity of that point at a section. So therefore at a section if we represent the specific energy, it will correspond to the depth of flow at that section and the average flow velocity at that section. So with that if I write ES is equal to H plus V square by 2G, then I can write one step further with the definition that Q, the flow rate, is equal to V into the width of the channel B into height, that is the depth of flow. So we can write that Q by V, Q by B is equal to VH. If we represent Q by B as small q, that is the flow rate per unit width, then Q is equal to V into H. So if you replace V in terms of Q by H, then we can write plus 1 by 2G into Q by H whole square. V square is Q by H whole square. So ES can be written as H plus. So this is a very important relationship among the specific energy with the depth of flow and the flow per unit with Q. Now in this equation we see there are three variables, ES, H and Q. So obviously from basic mathematical sense that out of these three variables, two are independent and one is automatically fixed by this equation. All right. Now if we try to find out what is the, now if we try to find out or we focus our attention in a particular fashion that the discharge is constant. Now how ES varies with H? If we see that how ES varies with H for a particular value of Q, that means if we plot this curve ES versus H with particular Q, what we will get? Let us draw this curve ES versus H. Now we see for very small value of H, this term will be dominant, where ES is inversely proportional to H, and at the same time when H tends to infinity, ES tends to 0. So this curve will be like this, small values of H, so that ES tends to infinity, H tends to 0. But at the same time when higher values of H, you see this term will be insignificant because this term will be smaller and smaller with H being higher and higher. So then ES becomes approximately equal to H, ES is equal to H. So it's a linear with a 45-degree line. That means if we draw a line ES is equal to H, that means this is 45 degree, then at the higher value the curve goes to asymptotically to this line ES is equal to H because the first term will dominate. So therefore we see the curve has a distinct minimum. That means there is a minimum value of ES for a given value of H. This is the minimum, ES minimum. So this is ES minimum. And the height corresponding to the minimum value of ES is designated as HC, and HC is known as the critical depth, height or depth, critical depth. So therefore we see the variation of ES with H for a constant Q shows a distinct minimum. So that at particular depth HC known as critical depth, the ES is minimum. If we decrease the depth, ES increases, which is because of this term, and if we increase the depth above this, then also ES increases because of this term. So this is the typical variation of ES with H. Well, the time is up, so we will discuss further in the next class. Okay, thank you.